One thing that I didn't say in the last video is why one would want to be a nanoengineer in the first place. And I hope you can tell from my shirt that I'm a huge nerd. And it is absolutely because I want to help bring sci-fi worlds to reality. I want to be able to cure diseases with a shot or a thought. I want the Iron Man suit. I want Spider-Man's web shooters. I want the transporter and warp drive. And based on the skill sets that I had developed as a student in chemistry and nanofabrication engineering and chemical engineering, or at least being part of a chemical engineering department as a postdoc, I feel that the center of all of that is in nanoengineering. And everything that's interesting to me about physics and chemistry, biology are all about processes that occur on the nanometer scale. So when you think about, like, why would somebody study this field of nanoscience, nanoengineering? Why would someone take a class in it? Well, sometimes they say, don't you want to learn the fundamentals first? Shouldn't you learn all about, physics and then, do these nano things? Well, take a look at the most important developments in technology in the last period of time. You have microprocessors with nanoscale features. You have vaccine delivery vehicles, cancer therapeutics, imaging materials that give you high contrast radiology images, for example. You have aircraft composite materials that are enabled by nanoscale materials and nanoscale engineering. And basically, all of that stuff is a product of nanoengineering. And most of the people who are doing that work, because there are not a lot of classes in nanoscience, definitely not a lot of degree programs in nanoengineering, those people doing that world-changing work learn to do what they are doing on the job and kind of by accident, because they weren't trained exactly in those areas. So what a degree in nanoengineering, or reading a book in nanoengineering, or taking a class in nanoengineering allows you to do is to skip to the end, skip to the cool stuff. And yeah, once you have the context in mind, your brain will be more primed to learn some of those fundamentals, like the topic of today's Nano Concepts lecture. So yeah, I think it's super important to be able to assume a lot of background knowledge without having to retrace absolutely everything in Newton and Maxwell. And you should absolutely go back to that fundamental piece of the learning pyramid. But why not learn where we can use this stuff first? It's sort of like asking someone in a sociology class, saying you can't take sociology or you can't get a degree in sociology without first getting a degree in psychology, and asking a psychologist that you can't study psychology without getting a degree in neuroscience, and then neuroscience, neurobiology, cell biology, and physiology, and then those people can't get their degrees without chemistry, and chemists can't get their degrees without physics, and so on down from discipline to anti-discipline. That is the discipline that comes before and informs the discipline. No, nonsense. You start where you're interested, and if that's a sociologist, you start in sociology. If that's nanoengineering, you start in nanoengineering. So we're giving you the power here to skip to the end. All right. Another point I wanted to bring up in the last lecture, but forgot to, was the the relationship between potential energy on one hand and force on the other. So this is the force, F of R, where R is the internuclear distance between two particles. This is R. And these two particles interact using an interaction potential energy that we call W of R. So force is the force, energy is the energy, and what is the relationship between them? It turns out that the relationship between force and energy is that force is the rate of change of the potential energy with respect to some distance. And in this case, the distance is r. It happens that to get the force to be attractive, to be negative, by convention, we need to add a negative sign out front. Don't let the dw dr be distracting or scare you. This is notation from calculus, and all that it means is that a little change in the energy and a little change in the rate. Actually, specifically, it means a little bit of energy and a little bit of rate of change. So, what does this mean? It means that if you have a positive and a negative charge. You have a positive and a negative charge. We know intuitively that there's going to be an attractive interaction. There's going to be an attractive force. So you have a positive and a negative charge. And as you bring them closer, so the R gets smaller and the W gets smaller. So you have negative over negative, because the R gets smaller, the W gets smaller. So negative dW over negative dr. They get smaller, they get smaller. This term, this part of the equation becomes negative over negative is a positive times a negative out front. So the force is negative. Negative force means attractive. The energy alone does not mean anything except in its relationship to a reference state. What are the reference states in nanoparticle or molecule or atom or ion referring to? Well, the reference state in this case is when they're infinitely separated. So the positive and negative charge have no interaction potential energy. It's all the same thing. We say energy, we say potential, we say interaction, all means the same thing. It's zero here, and maybe it's negative here. So you go from 0 to negative, you're decreasing in energy or potential or interaction energy or whatever you want to say, while the R decreases. So dW over dr is negative over negative is positive, and that you have a negative out front, that means it's attractive. Now, how do some of these forces arise in nanoscale and molecular systems? So the first one we have is where our two particles are positive or negative, and this is Coulombic interaction, and that just is Coulomb's law, which is negatives and positives attract and positives repel. Number two, we might have, so Coulombic I should say is ion. Then we have ion dipole. What is a dipole? A dipole is two charges or two partial charges that are stuck together, usually by chemical bonds. A good example is water. Water looks like this. Oxygen is very electronegative. It also has two lone pairs. Remember the Lewis dot structures from your high school chemistry class. And the dipole moment points this way, where U is the dipole moment. And then if you have an ion, say you have a sodium plus, then there's going to be an interaction between the positive sodium ion, and the negative charges, the partial negative charges of the oxygen. Number 3 is dipole. So dipole means two dipoles interacting with each other. So instead of the sodium ion up here, you have another water molecule, and that other water molecule has its dipole moment also oriented in the same direction, and this hydrogen atom is associated through, in this case, something called hydrogen bonding, which is an especially strong form of dipole-dipole interaction, and this interaction can persist for a short time, very small fractions of a second, and then they find other dipoles to interact with. And what's special about the dipole-dipole interaction is that these molecules don't need to be locked in place. They can be flopping all over the place. But the key is, if my elbow is the negative side and my hand is the positive, or is elbow negative, finger positive, it's more likely to be in an orientation where the dipoles are aligned, but they're still free to rotate. However, as you raise the temperature, you get a lot more motion, right? Temperature motion. And that dipole, and then there are fewer interactions, fewer orientations where the dipoles are aligned on average. So there's a T dependence. Temperature dependence. It decreases with T. Number 4 is dipole-induced dipole. Dipole-induced dipole introduces another concept. So in an interaction where we have atoms and molecules that have electrons buzzing around, those electron clouds can be deflected or moved in the presence of an electric field. So if you have a nucleus where we have this electron orbiting the nucleus, say this is a hydrogen atom, and you apply an electric field, and the electric field is oriented like this, where this is the positive end, this is the negative end, this is our electric field, then this orbit is going to shift over to the left to lower its overall energy. So the negative will now be shifted over this way. Kind of goes like this if this is your electric field. And this is called an induced dipole. Now, a permanent dipole, like water, can influence the electron cloud in a nearby atom or molecule, thus making it an induced dipole, and then they can interact by a dipole-dipole interaction. Importantly, you can have a dipole-induced dipole interaction on top of a dipole-dipole interaction. So say you have these two water molecules. This permanent dipole is not only interacting with the other permanent dipole here, but it's also inducing a dipole by these electrons here are pushing the electron cloud of this water molecule over here. So it's like electrons, and then these electrons, this negative charge part of the water molecule is pushing those over, and then you get another dipole. So you get the permanent dipole plus the electron-induced dipole. So this is how dipole-induced dipole and dipole-dipole can exist on top of each other. And finally, and there are other sort of middling categories, but this is the basic idea, you have dispersion. Dispersion forces, named after London, the person who first described dispersion forces. And dispersion forces are due to the fact that these electrons that these electrons orbit with some orbital frequency. So you have this positive charge here, and this is the nucleus, and then this is the electron. And the electron orbits. Now, it doesn't really orbit like a planet. It more like resonates. It kind of goes, and it forms a cloud. And that cloud has a probability density that, for a hydrogen atom in the ground state, is spherical. And it has kind of a radial distribution function where it's kind of like more probable right here, where I've drawn this. And then that function, it's called a wave function, decays out here. So a hydrogen atom, the wave function actually exists, imperceptibly, but actually kind of extends quite a long way away from the nucleus. But anyway, its maximum probability is in this circle. Now, even so, even though it is technically buzzing around really, really fast, we can still say, all right, if you were able to take a snapshot of that electron orbiting the nucleus, you would be able to say it's here, let's say at T1. And then you would have a dipole moment vector that looked like this. But then you take another snapshot and it's over here now. And now your dipole moment vector looks like this. And this is T2. And then you take another snapshot and it's at T3. And your dipole moment vector is like this. Now, each one of these instantaneous dipoles is capable of interacting with the electron cloud of a nearby molecule, like this, and pushing that electron cloud away. So it's the electrons orbiting all of this whole molecule, and the instantaneous dipole here is interacting with an induced dipole that it creates in a nearby molecule. And so this is dispersion. And so what we have is dispersion, which exists all the time, plus a dipole-induced dipole interaction, plus a dipole-dipole interaction, in the case where you have two dipoles. If you have only one dipole, which say you have oil and water interacting, a molecule of oil and molecule of water, and that oil molecule is not polar. Say it's a linear hydrocarbon, just CH3, CH2, 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 CH3, something like that. Or methane, CH4, or a noble gas like krypton or argon. You would have a dispersion force because every molecule and every surface and every nanoparticle has a dispersion force with everything else in its surroundings. And it also has a dipole-induced dipole. But because you have water and something that's nonpolar, you do not have the dipole-dipole interaction. Now suppose you have two nonpolar molecules, say a molecule of methane interacting with a molecule of argon. In that case, you have the dispersion interaction, but you do not have the dipole-induced dipole interaction. So in this case, the hierarchy here, it's layered. You always have this, you sometimes have this, and you sometimes have this, but you can't have this without this and this. You can't have dipole-dipole without dipole-induced dipole and dispersion. You can't have dipole-induced dipole without dispersion, but you can have dipole-induced dipole without dipole-dipole. And now that I've totally used the word dipole way too many times, we will end there. I'll see you in the next episode. Oh wait, I totally forgot to say that number 3, 4, and 5, dipole-dipole, dipole-induced dipole, and dispersion are together called the van der Waals force. And the van der Waals force is recognized by the fact that the potential energy decreases with 1 over the distance of separation to the 6th power. So anytime you see 1 over r to the 6th or anytime r to the sixth is in the denominator, it is 99.99999% chance going to be a van der Waals force. So together, these three are the van der Waals force. Probably we should spend an entire year talking about van der Waals forces, but everyone would be upset about that. I think it's super important because it makes up all of the interactions that are interesting in biology and material science, and anything related to organic media. So that's polymers, vesicles, paint formulations, plastic materials, biomaterials, biology itself, self-assembly, any of that stuff all involves number 3, 4, and 5. Really important stuff. Okay, now I will see you next time.